All right, hello guys, and today we're going to be looking at the graphs of tan functions. So, the trick about tan functions is they involve asymptotes because if you remember that tan of x is equal to sine of x divided by cos of x, which means that when we have cos equals 0, then that means that there's an asymptote. So, for cos of x, when is cos of x equal to 0? What values of x in radians are when cos of x equals 0? So again, think about our good friend Mr. Table. So pi over 2 I'm seeing in here. So there's our magic truth table. And it says here, tan is undefined when cos is pi on 2. All right. So if cos of x is equal to 0, then tan of x is undefined. So what that means is that we are going to have asymptotes every single time that cos of x is equal to 0. Which means that we will have multiple asymptotes. So I'm going to quickly do an axis. So I've got a ruler here, and it says so if I mark this out as this is 2 pi, this is pi, this is pi on 2, and then this will be 3 pi on 2. What this relationship in this table says is that at pi on 2, I'm going to have an asymptote. Now, because it's a circular function, the graph is going to repeat itself. And what that means is that the graph is going to have another asymptote, and then another, and then another. So the question is, where do you think the next asymptote is going to be? Think about your circular functions and think about how often cos is equal to 0. I'm seeing a 3 pi on 2. That is correct. So the next one is at 3 pi on 2. So the question is, how often do these asymptotes appear? What's the frequency of these asymptotes? How often do they show up? Pi. So, if the asymptotes are showing up every single pi, what does that tell you? What does that tell you about the period of a tan graph? If the asymptotes are repeating every pi, what does that mean the period of a tan graph is? One what? How far is it from here to here? That's pi difference. So therefore the period is just pi. So for tan AX, pi on n, or pi on a. So that means that if there's no value in there for a, then that means the period is just pi on that number. So if I were to make it 2 pi, then that means the asymptotes would appear twice as often. Which would mean you'd have one at pi on 2, one in pi, and 3 pi on 2, and 2 pi. So, what does this graph actually look like in practice? Now, we have some exact value tables here that we can work with. So it's saying pi on 2 is that. Pi on 3 is root 3. Pi on 4. So let's actually mark this out. So halfway between, so this is 0. Halfway between 0 and 2 pi is what? Pi on what? What's halfway between 0 and pi on 2? Pi on what? What number's there? Pi on 4. There we go. So that's pi on 4. And where does it say pi on 4 is? Pi on 4 is at 1. So we'll arbitrarily call that 1. And then let's go a little bit shorter. Let's go to pi on 6. So now that's going to be, we divide this into thirds. So pi on 6 is going to be about here. Now I'm not being super accurate, but it says it's 1 on root 3, which is 0.8-ish. Yeah, no, pi on 4. Yeah, pi on 6. Yeah, not pi on 3, pi on 6. And then pi on 3 is going to be root 3, which is about 1.7. So, if we were to actually connect these up, because remember at 0, it's 0, the graph looks a little bit like that. But that's only this one bit here. Now, if we were to go through and we were to repeat this, if we were to add pi to everything, everything would just repeat itself again. And the graph would go up like that. And then it would go up like that and go up like that. Now, that doesn't explain what happens here. Once we go past pi on 2, what quadrant are we now in? Remember your CAST. So we start at 0, we have pi on 2, 3 pi on 2. Yeah, so now we're in quadrant 2. Because we're in quadrant 2, what does that mean all the tan values are going to be? They're all going to be negatives. So, what we have is we actually have this upside down. I can probably draw that a little bit better. And then as you can see, the graph basically, it's a mirror inversion of what's going on here. So here will be your pi on 6 from pi on 2, pi on 4 from pi on 2, but it's all going to be in negatives. And then once I get past 3 pi on 2, that negative bit repeats itself again. Because, again, this is quadrant 1, which is A. This is quadrant 2, which is S. This is quadrant 3, which is T. And this is quadrant 4, which is C. So in quadrant 4, everything's negative. Quadrant 2, everything is negative because it's S. But in quadrants A and T, as in 1 and 3, the values are going to be positive again. And this is just going to repeat itself over and over and over again. All right? So, we know that if we were to look at the solutions for this graph, the solutions for this graph are going to repeat themselves every pi because the period is pi. Now, we can also stretch by putting a dilation on the graph. Same way with that we can manipulate sine and cos. So we can stretch them up, or we can change the period to squash them together. So when you do a tan graph, it is going to shift where the asymptotes are. As long as you know where the asymptotes are supposed to be, you can draw that general shape of the graph unless there's a dilation, and that will make it much, much easier to draw your graphs. So what we can do is, let's do a practice question with a period shift. So I'm not going to bother using a ruler to do this next bit. Oh, actually, maybe I should, because that's just awful. Oh wow, that's bad. Now, the same thing, if you guys remember when you did hyperbolas, what doesn't the CAS draw for you when you do a hyperbola on your CAS? What doesn't it draw for you? Yeah, so it doesn't do the asymptotes for you, which means that once again, you are going to have to make sure that when you are doing your graphs, you put in your own asymptotes. All right? Because otherwise, it's going to not look right, because you're expected to mark all your asymptotes. So if I do, for example, y equals 10 of 2x. Our formula states that we will have asymptotes every period. The period is not pi anymore, it's pi on n, which means that the period is pi on 2, which means that we will have asymptotes every so often. So the question is, where are they going to be now? So if the period is pi on 2, that means the whole graph will repeat itself inside pi on 2, which means because of the way circular functions work, we know that they're going to repeat. So the question is, how do you know that there are asymptotes every single period? It is a tan graph. A tan graph is made by a sine graph divided by a cos graph because there's a certain frequency that cos is equal to 0. That means that it's going to take the period of that graph and go, well, okay, if it's 0 this many times, and that means every time there's a 0, there's going to be an asymptote. So it takes it into the tan graph. So it used to be that there was one every pi. Now there's going to be one every pi on 2. So straight away, we can mark that we're going to have a lot of asymptotes. So the asymptotes this time are actually going to be, it's not going to be here because they were here to start with. But because the graph repeats itself, we have to go halfway. And that means our asymptotes are actually going to be halfway between. So it's now going to be at pi on 4, 3 pi on 4, 5 pi on 4, and 7 pi on 4. And that means that our graph will have to repeat itself now. Obviously, when you guys do it, you're going to have rulers and you're going to have stuff like that. I don't have that luxury on here. So now, as you can see, the graph is completely squished. So normally, in a sine graph or a cos graph, the period is 2 pi. But in a tan graph, inside 2 pi, the graph repeats itself twice. So if I ask you to draw one period of a tan graph and you give me 0 to 2 pi, that's probably not going to be the answer you want. All right, so when we are asking you about finding specific things for your graphs, it is going to be very tricky if you forget that for a tan graph, the period is pi on n, not 2 pi on n. That is one of the major differences between sine and tan and cos. So if you remember your basic tan graph, you can very easily do period changes by simply taking the n value and just running it through all the other pieces of information. So 0 divided by 2 is still 0, so there's an intercept still there. The first intercept after that is going to be pi divided by 2, which is pi on 2. The second one is going to be 2 pi on 2 divided by 2, which is pi. So I've just simply smushed everything together. And at the same time, if n was a fraction, so for example, it was 1 on 2 times x, then I would be stretching the entire graph out, and it would take 2 pi for the graph to start repeating itself. When you are doing solutions with these, it works exactly the same as doing a tan or doing it with sine and cos in terms of you moving things around. The only difference is that the graph looks very different because of the asymptotes. So, in your book, there is a lovely table that helps you to remember what these are. I'm going to put it on the screen for you now. All right, and this is straight out of your textbook. In general, for all positive numbers, the graph of tan A tan nt is obtained from the graph of tan t by a dilation of that to that. The period is pi on n. The range is infinite. And then the asymptotes follow that pattern. 2k plus 1 times pi divided by 2n. So n comes from the equation. K is the first asymptote. Where is the first asymptote? Where is the second asymptote? Where is the third asymptote? So what you do is you just replace a number, or k with a number, and it will tell you where it is. So where is the first intercept going to be? Or where's the first asymptote going to be? Well, you start at 0. The first asymptote would be at 0. So k is 0. So 2 times 0 plus 1 is just 1. Pi on 2. The first asymptote is at pi on 2. The second one, if we add plus 1 to it, etc., etc., etc. So if you have that table available to you in your workbook for your notes, it should make your life much, much easier. All right, so I need you to go now have a look at 14L and see how you go with that.